Hello friends, in this video I will explain the basic concept of work done. Okay, so what exactly do you mean by work done? We are not talking about the homework or classwork or the kind of emotional work that we are doing. We are talking about the work done in the manner of physics. Okay, so here two ingredients are essential for the concept of work done. One is force and other is displacement. Now, who does the work? It is always some force who is doing the work. Okay, such as who is doing your homework? It is not a force which is doing your homework, it is you, right? So, that kind of work done is not included in the concept of work done that we are learning right now. Okay, who is doing the work? It is always a force which is doing the work. And what is the result of work done? That we always get some displacement of a massive body. Okay, so who does the work? It is the force which does the work. And what is the result of that? The result is displacement. And very simple, the calculation of work done is simply given as vector F dot vector S. Now here we are taking the dot product because work done is a scalar quantity. Now this is another matter of discussion, that why work done is a scalar quantity, because force and displacement, both of them have directions. So how can they produce a physical quantity which is not having any directions? See, my friends, work done is not only used to cause displacement, but it is also causing the change in size and shape of the body. Okay, when we learn advanced level physics, we will know that the change in size and shape of the body is also caused by work. So, in that case, there is no displacement of the body. And because of this, we cannot assign any direction to work done. So, work done is treated as a scalar quantity. You can see in this example, given on the left side, is a man who is trying to push a heavy body. The force is being applied and the body is undergoing displacement. So we can say that the work is done. But if suppose the mass is very heavy and the person is not able to move it, it is like you who is pushing a wall, but the wall is not changing its position. So there is no displacement. So even though force is applied, but because displacement is nil, we do not say that any work is done in the second case. Now the question arises, how do we calculate work done by different methods? See, the very simple formula to calculate work done is to take the product of force and displacement. What kind of product you are taking? You will be taking the dot product. Okay, now suppose if the force on the displacement are very small. Okay, it is so small that you cannot observe it, but you can measure it by very delicate instruments. In that case, the work done is calculated as dw is equals to vector f dot ds. Okay, now see here in this equation, the work done is small because the displacement is small. In this equation, I can never take force to be small, right? Because see, if there is a very heavy body of say 50 kilogram and it is displaced by a small amount, say 1 millimeter, then the displacement can be small. Try to push that same body by using small force. The force will never, if the force is smaller, it will never be able to displace that body. Okay, so when you are using the differential equation of work done, never make the force small. It is always displacement which becomes small. Now the third technique. So in the second technique, you will learn how to calculate the work done, the small work done. Okay, now to sum up or to calculate the huge work done by using variable forces, or to sum up the total work done, the total work done is integration of small work dones. Integration means to collect the things, to add up the things. So what we are doing, the calculations is like this. First we calculate dW and then we integrate dW. That is nothing but integration of F dot ds. So by this third method, we can find the total work done. And now the last method, which is graphical method. Now I have drawn a very simple graph of force versus displacement, right? Now in this, if I calculate the area of the graph, I will have to multiply the dimensions of force and displacement. And very simple, if I multiply the dimensions of force and displacement, what do I exactly get? Exactly, I will get the work done. So now if you have understood the basic concept of work done, okay, let us discuss that in which of the cases the work done will be 0. The first case, if F is equals to 0, the work done is also 0. Now let us understand this first equation, F is equals to 0. Okay, see, if a body is moving with some constant velocity, without changing direction, without changing the speed, its motion is uniform. Okay, and if it is moving in outer space, what is the force acting on the body? There is no force acting on the body. But is the body getting displaced? Yes, because it is moving with uniform velocity. Each and every time it is getting displaced. But here there is no force. So is there any work done to move that body? No, the work done to move that body will be 0. That means to continue the uniform motion of any body, you always need the force to be 0 on that body. Alright, so if force is not applied, the work done becomes 0. In the second case, displacement is 0. Now this is something very simple to understand. Try to push a very heavy body. The displacement does not take place, and because displacement becomes 0, the work done becomes 0. Right? And the last case, in this balloon, theta equals to 90. What is the expression for work done? It is Fs cos theta. Now if theta equals to 90, cos theta equals to 0, and therefore work done is also equals to 0. Means if force and displacement are perpendicular to each other, then the work done by such a force will always be equal to 0. Now this reminds me of a force known as centripetal force. Right? You can see in the last balloon, I have given an example of circular motion where the displacement, the immediate displacement, or you can say the instantaneous displacement of the body is shown. The force acting on this body is centripetal force because it is moving in circular motion. The angle between force and displacement here is 90 degrees. Therefore, the work done here also will be equal to 0. Clear? Means that centripetal force does not do any work. Actually, centripetal force is necessary to keep the body in circular motion. What is the work done by that centripetal force? The work done by that centripetal force always remains 0. Quite somewhat difficult to digest, but it is actually true. Consider this example now. The coolie standing on the left is carrying a heavy luggage on his head, but he is standing. He will be wasting his energy because all the time he is lifting that heavy luggage, but actually the work done by him is 0. Why is that so? It's because the displacement of the luggage will be 0. Okay, so actually if you ask him, did you do any work? He said, yes, I have done a lot of work. I'm holding this luggage on my head for a long time. I'm getting tired. My energy is getting waste. I am perspirating. But if you ask in terms of mechanics, in terms of physics, the work done by the coolie on the left will be 0. All right. Now consider the second coolie who is moving towards right hand side, and again he is carrying a heavy luggage on his head. All right, what is the work done by that coolie in the movement of that luggage? We note the direction of forces. See, the movement of luggage is in this direction, and the force applied by the pulley on the luggage is in upward direction, right? Clear? The pulley applies a force on the luggage in upward direction, because if that force is not applied, the luggage will come down. So the force of pulley on luggage is in upward direction, but the displacement of luggage is in horizontal direction. So what is the angle between both these forces? Both the force and displacement? It is 90. And therefore, the work done by this pulley is also zero in terms of physics. Now coming to the last example, this is Sun, the center of our solar system, and this is Earth. Okay, this is the Sun and this is Earth. You know that which force pulls the Earth towards the Sun? It is the centripetal force. Which force plays the role of centripetal force over here? It is a gravitational force between the Earth and the Sun. And because of that, the Earth moves in circular motion. Okay, talking about the instantaneous displacement of Earth, it is in this direction, and the direction of gravitational force, or in other words, say centripetal force, is towards the Sun. Again, the angle between instantaneous force and instantaneous displacement is 90. So the work done by this force also becomes equal to 0.